Hello, everybody. This is the first of two screencasts for section 6.1 and 2 on inference for proportions. You're going to need to make sure that TigerStats is attached in order to do our work. So run that in the console if you have not done so lately. In this set of slides, we're going to cover inference for one population proportion. And you might think, well, we did that in chapter 5, but we're going to show you some streamlined methods that you would use in production in real life rather than the kind of by hand calculations that we used in chapter 5 to introduce the concept of confidence intervals and hypothesis testing. So let's start with the research question. Are a majority of Georgetown College students female? And we'll use some data that's already been gathered and is in a data set prepared for you, the M111 survey data. So we've looked at it many times before, but if you need a little review, get a view of M111 survey and some help on M111 survey. And just to model that, I'm going to go ahead and copy and paste into console of RStudio. And so we get the view up here. And of course, one of the variables is sex, which could be either male or female are the values for these 71 students. And I'm wondering why I'm not getting help. Try that again. Oh, there is a misspelling. So I will need to correct that in slides. And sure enough, here is the help. Okay, good to know. So if we are interested in this question, we need to get ready to answer it by looking at what's in our data on the sex of students in the survey. So going back to early in the course, when we're looking at categorical data, tally can help us. We can tally the variable sex here after the twiddles. Just have to mention the data set where it lives. And that's where we find that 40 out of the 71 students in the sample were female. So a majority of the students in the sample were female. But is that strong evidence that a majority of students in the population of all Georgetown College students are female? That's our question. So go ahead and get the sample proportion. That's the 40 divided by 71.563. And let's go ahead and think about the population parameter of interest. It's a population proportion, so we'll call it P. And in words, it's the proportion of all Georgetown College students that are female. Note the emphasis on all. It's that whole population, not the sample. We know about the sample. Now, we don't know P. But if P is bigger than 0.5, then a majority of Georgetown College students would be female. And so our research question really turns on the value of P. So why don't we set up, why don't we go ahead and make a 95% confidence interval for P and do a test of hypothesis where the null hypothesis states that P is right at the boundary between a majority and a minority of Georgetown College students being female. And the alternative hypothesis just disagrees with that. Now, back in chapter 5, we went on to compute a test statistic using a z-score for the sample proportion, and we used the normal distribution to approximate p-values and also to form confidence intervals. But In the case of one population proportion, we actually have more direct methods that don't rely on approximations. And one of them is the so-called Klopper-Pearson procedure that the text mentions but doesn't really cover. We're not going to cover the math behind it, but we'll show you how you can implement this method in R. So just reviewing, we have a fixed number of trials. Every person is like a trial, and each trial had two possible outcomes. The person could be a female or male. And every time you picked a person from the population, they had a P chance of being female. We just don't know what P is. And those trials are independent of each other because we're doing random sampling. So when we learn one person turns out to be female, it doesn't affect our estimate of the chances of like the next person being female. So those four things here are the four conditions for being in the binomial situation. And so that means the count of females in the sample is a binomial random variable. And the sample proportion p hat is that count divided by n. So really, the sample proportion is very closely related to a binomial random variable. All that probability that we know about binomial random variables must somehow apply, and that's what the Klopper-Pearson method basically handles for us. So this is implemented in a function called binomtestGC in the TigerStats package. So what you do is you just name the variable that you want to study after it twiddles. You name the data set that it comes from. You do need to say which of the two values in your sex variable you're actually counting up, what counts as a success. So you do that with this parameter success. You just say the value in quotes. Now you're planning to do a test of hypothesis, so you need to tell R what the null hypothesis thinks that P is. And so you use a parameter called P for that. The null value is 0.50. And just for fun, we're going to get a graph of the P value with graph is true. So I'm going to go ahead and copy and paste and run this code over in RStudio, and then we'll take a look at the output bit by bit. So copy down in the console, and here it comes. It should give you lots of room here. Maybe increase the size a bit. And these are the results here on the left in the console that you would study to form the rest of the test. Over here is a graph that we'll talk about in a bit. So when you look at the beginning of the output, it's kind of like the prepare part of a hypothesis test. You're just kind of setting up and looking at what the data says. And we got 40 successes in our 71 trials because 40 of the 71 people said they were female. And then we go on to some inferential results. That's the confidence intervals and the hypothesis tests. We first give the point estimate. That's the sample proportion. So our best single guess at the proportion of all females at Georgetown College, our best single guess at the proportion of all Georgetown College students who are female would be 56.34%. That's our best guess. But then we report the standard error for p hat. It's about 5.89%. So our best guess could easily be off by 5.9% or so. And we see a 95% confidence interval for the unknown population parameter P. You get a 95% confidence interval by default. And it runs from 44% to 68%. So if you had to report this interval to someone and interpret it, then you could just show your interval here. And your interpretation would be to say that based on our data, we are 95% confident that P is somewhere between 0.44 and 0.68. Or we could say we are 95% confident that the proportion of all Georgetown College students who are female is somewhere between 44% and 68%. Now, what does that mean for our research question? Our research question is, are a majority of Georgetown College students female? Well, the cutoff value between majority and minority, that null value, is inside of this interval. There are values less than 0.5 that are in the interval, and there are values more than 0.5 that are in that interval. There are minority female values. There are majority female values in the interval. Well, since there are minority values in the interval, it's reasonable, based on the data, that one could believe that a minority of Georgetown College students are female. We just can't rule out the idea that half or a minority might be female. The null value is inside the interval. Now, let's take a look at how the hypothesis test is handled. When you look back down into the output, after the confidence interval here, you'll see test of significance and a statement of the null and the alternative hypotheses. P equals 0.5 is the null. P is not equal to 0.5 is the alternative. Exclamation equal means not equal. Now, remember, there's also a check step in hypothesis testing. Is this p-value going to be accurate? And the check holds for confidence intervals too. You just wonder, are these intervals really, do they have the level of confidence that they claim to have? Back in chapter 5, that was all dependent upon the normal approximation being reliable. But in this procedure, there are no normal approximations being made, no approximations of any sort, in fact. So there's no real need for a check. You can always trust your results, no matter whether the sample size is big or small. But with this caveat, you need to have taken a random sample from the population. That's always the case. As far as the compute step of the hypothesis test, where you compute the test statistic and the p-value, the test statistic's really easy this time. There's no z-statistic that you compute. The test statistic is just the number of successes in your sample, so it's the 40. And the p-value is computed mathematically for you, and turns out to be 0.3425. So you'll see that p-value right underneath. It's the last thing that's shown in the output. So I want to tell you a little bit more about where that p-value comes from. It comes from a two-sided probability that's associated with that underlying binomial distribution, the one with 71 trials, and chance of success set equal to the null value of p equals 0.5. And so a graph of that is actually shown over here because we said graph is true when we called binomtestGC. Let's take a look at that graph here in the slides. So what happens is the 40 was the test statistic, and we look at all of the possible values for the binomial random variable 40 or higher, but also all of them that are 31 or less. And basically, that's all the rectangles on the other side that have a height less than or equal to this 40 rectangle height here. And you sum those two together. The reason for taking both sides is that before we took the sample, we really had no idea as to whether the data was going to show a majority or a minority. And so we're kind of being fair and even-handed about it. All of our hypothesis tests are two-sided. So interpreting the p-value is the really important thing. A computer will get it for you, but it's up to you to tell other people what that number means. And so you use the template for interpreting p-values that we learned in Chapter 5. And that template is always, if the null is right, then there is about a p-value chance of getting results at least as extreme as the ones we actually got in our data. So here we would say, if the null is right, if p is really just 0.5, neither a minority nor a majority, then there's about a 34.2% chance of getting a sample proportion of females that's at least as extreme, as far from what the null expects as the one we actually got. I mean, if you think about it, the null is expecting about half of the 71 people, that's 35 and a half, to be female. We got 40. That's more than what the null expects. This p-value is saying, well, what's the chance of getting at least that far away if the null is right? And it's not a very small chance. In fact, since the p-value is bigger than our standard cutoff level of significance, 5%, we're not going to reject the null hypothesis this time. So our conclusion, you always want to write a little short, simple one-sentence conclusion, is that this data did not provide strong evidence that a majority of Georgetown College students are female. So notice in comparison to Chapter 5, when you are doing a binomtestGC for one population proportion, there's really only 3 steps to the hypothesis test procedure. That's the prepare, the calculate, and the conclude. There's no elaborate check step because the normal approximation is not used, but as in every statistical situation, we're assuming that you have taken a random sample from the population, not some biased sample, and so that always needs to be thought about. After all, if our sample was a sample of, say, Kappa Delta students from Georgetown College, that would be a very biased sample of the population. It would only let in those sorority members, and our data on the sex of students would be really, really skewed. So let me show you another example involving a question about one population proportion. This one is from a Gallup poll, and polls actually done, on feelings about impeaching Donald Trump that people had last year. So you could, if you're following the slides, you could click here for a link to the Gallup article. When you read the article, you'll find that Gallup took a random sample of 1,526 United States adults and found that 52% of them favored impeaching Donald Trump. Does this poll give strong evidence that a majority of all U.S. adults favor impeachment? That's our little research question. So let's find out. Let's get ready, prepare a test of hypothesis. We need to define a population proportion. Let's let P denote the proportion of all U.S. adults who favor impeachment, or who favored it back when the poll was taken. And again, two hypotheses. This is another majority-minority question. There are a lot of that type of question when you're working with proportions. Null hypothesis is just going to say P is at the cutoff. Alternative will disagree. But this time, we don't have our data in a data set somewhere. We've just got this summary data that we got from this article on the web, the 52% out of the 1,526 people. So how are we going to proceed from here? Well, we're going to need to find the number of people in the sample who favor impeachment. We only know the percentage. Turn that into a proportion, 0.52, and multiply by how many people were in the sample, and you get 793.52. Let's round that off. My thinking is that 794 people out of the 1,526 must have said, yes, I favor impeaching Trump. Now, once you've got the number of successes, the number of yeses in your sample, along with your sample size, you can use binomtestGC, but you're not going to use it the same way we did before because you're not looking inside a data set. Instead, you're going to feed it summary data. There's a parameter x that you set equal to the number of successes, the number of yeses in your poll. There's a parameter n that you set equal to the sample size. And if you want that test of hypothesis, you've got to give a null value with the parameter p. And just for fun, again, we'll do graph equals true. So let's go ahead and copy paste and run this in our studio. Here we are. So we'll be looking through these results. So I want you to think about this for a bit. You could stop, the slides and go ahead and run this and think about it. Or I'm going to transition back to the slides and you can look at it there. But looking at the output, try to answer two questions. Based on the confidence interval for P that's shown, does the poll definitively show that a majority of all U.S. adults favor impeachment? And based on the p-value, does the poll definitively show that a majority of all U.S. adults favor impeachment? So let's take a look. Here's our best guess. That's our sample proportion. Best guess at P, 52%. That guess could easily be off by 1.3% or so. The key is the confidence interval. It extends from 49.5% roughly to 54.5%. So the null value of 0.5 is inside that interval. That means that there are going to be some minority values inside that interval. All the values from the 49.5% to the 50% are minority values. They're in that interval. They're reasonable values based on the data. It's not just the majority values from 50 to 54%. So based on the confidence interval, I'd say we don't have strong enough evidence to conclude that a majority of the population favors impeaching Trump. And let's see if we can get the same thing from the test of significance, test of hypothesis. Well, the p-value is 11.84%. So if exactly half the population favors impeaching Trump, there's about a 12% chance of getting results as far away from 50% as what we got. That's not a terribly small chance. I mean, I'm a little suspicious that maybe p is really bigger than 0.5, but this p-value just isn't small enough to convince me. It's bigger than our cutoff of 0.05. So I wouldn't be rejecting the null hypothesis in this case. We got some evidence, but not really strong evidence, that more than half of Americans favored impeaching Trump at that time. So that's the kind of thinking you will do with your output, and that informs what you would write when you do a report involving confidence intervals and tests. Next time, in the next screencast, we'll look at inference for cases where you've got two populations and you're interested in the difference of two proportions in those populations. See you soon.